All right, we are starting Unit 10 today with some exponential functions and their graphs. So first, what is an exponential function? Well, it's a function f with base a, where f of x equals a to the x power. So that a that's attached to your exponent is called the base. And a is always positive, and a cannot equal 0. So when a is greater than 1, we have exponential growth, an increasing graph. And when a is less than 1 but still positive, we have exponential decay or a decreasing graph. And the reason that we exclude base a of 1 is because 1 to any power will always be 1. So that would just look like the horizontal line y equals 1. So it will not hold the same shape as your exponential functions. So it has to be another value. So we're going to first take a look at these different graphs, and we're going to start with a parent function and then look at some transformations and look at what happens with our domain, range, increasing, decreasing behavior, y-intercept, and horizontal asymptotes. So starting with this parent function, 2 to the x, well, when x is 0, anything to the 0 power is 1, so I know I'll have a point there. 2 to the first power is 2. 2 to the second power is 4, and 2 to the third power is 8. So there are 4 points that I can graph and connect the dots on to make my exponential parent function that we're going to reference. And this is the parent function, so I don't have any transformations to reference just yet. The domain of this function is all real numbers. My range is that y is greater than 0. It is an increasing graph. My y-intercept is at 0, 1, and I've got a horizontal asymptote at y equals 0. So keeping all of this in mind, moving on to number 2, I've got 2 to the x minus 3 power, which tells me this is a transformation moving 3 units to the right. So I'm just going to take those 4 points that I had on my first graph and shift each of them to the right 3. And then again, I can connect the dots. And here is my new transformed function. The domain is still all real numbers. My range is still that y is greater than 0. I still have an increasing graph with a y-intercept that has changed now. So to figure out what that y-intercept is, remember that's when x equals 0. So this would be 2 to the 0 minus 3 power, which is 2 to the negative 3. So that would be 1 over 2 to the third, or 1/8. And then my horizontal asymptote is still at y equals 0. Moving on to 3, if we're referencing that parent function from number 1, this will have shifted down 3. So I'm going to take those 4 points from number 1 and shift them each down 3. And then I can connect the dots. The domain of this function is still all real numbers. My range now is that y is greater than negative 3. I am still increasing. My y-intercept has now moved to 0, negative 2. And my horizontal asymptote is now at y equals negative 3. Looking at number 4, that negative on the outside tells me that we are reflecting over the x-axis. So I'm going to take that graph from number 1 and flip it upside down. Connect the dots. And here is my transformed function. The domain of this graph is all real numbers. My range is that y is less than 0. My graph is decreasing because if I were to be walking from left to right, I'd be going downhill. My y-intercept is at 0, negative 1. And my horizontal asymptote is still at y equals 0. On graph 5 here, the negative being on the exponent tells me that I'm going to be reflecting this one over the y-axis. So I'm going to take that graph from number 1 and kind of mirror it. And then I can connect the dots and draw my exponential function that still has a domain of all real numbers, a range of y values greater than 0. It is an increasing graph. My y-intercept is at 0, 1, and my horizontal asymptote is at y equals 0. And then last but not least, number 6, this one's going to look just like 5, except I'm also shifting up 2. So this is a reflection on the y-axis and a shift up 2. So I'm going to take these points from 5 and just shift each of them up 2. Okay, so the domain here is still all real numbers. My range is that y is greater than 2. I have a decreasing graph. I have a y-intercept at 0, 3, and a horizontal asymptote at y equals 2. So when you're graphing these functions and you're just given the equation, think about your parent function and what kind of transformations are taking place to help you determine what it's going to look like and how that changes these different characteristics. So in summary, what we have looked at here is when I have my parent function, a to the x power, my domain is all real numbers, my range is all positives, my y-intercept is at 0, 1, I have an increasing graph and a horizontal asymptote at y equals 0. And again, with it being increasing, that means that this is exponential growth. Now, what changed when my x became negative, like on 5 and 6? Everything stayed the same except that my graph became decreasing. So when I have a to the negative x, my domain was the same, my range was the same, my y-intercept was the same, but I had a decreasing graph, which we could also call exponential decay. And if we look at a to the negative x, that really means 1 over a to the x, which is when you end up with a base that is less than 1. So now we're going to look at how I know if I have growth or decay by just looking at my base. So on this first one, remember the base is the number attached to your exponent. Here it's 5, that's greater than 1, so I know that this is going to be growth. On the next one, my base is 1/4, that's less than 1, so that's going to be decay. I've got 11 over 4, which is a fraction, but it's still greater than 1, so this is going to be growth. And then on the last one, 0.6 is less than 1, so that is also going to be decay. So now how do you write and solve your own exponential growth and decay functions? Well, you've got really one formula that you kind of alter depending on whether you are growing or decaying. Your function is going to be a, your initial value, times 1 plus your rate of increase if you're increasing to the t power, where t is time. And if it's decay, it's the same except you're going to do 1 minus that rate of decrease. So let's look at a few examples of that. For this first one, the original value of an investment is $1,800. That's your A value. If the value increases, that tells me that this is going to be growth by 7% each year. That is my R value. Write the exponential function to model the situation. So I'm going to do growth. Y will be equal to 1,800 times 1 plus 0.7 to the t power. So that's 1,800 times 1.07 to the t. And then if I want to find the value of the investment after 15 years, well, I'm just going to substitute 15 for t. So 1,800 times 1.07 to the 15th power. You'll use your calculator for that, and we're talking about money, so you're going to round to 2 decimal places here. And that'll be approximately $4,966.26. Moving on to the second example, in 2002, there were 972 students at this high school, and the number of students increased by 1.5% each year. Again, increase tells me that this is going to be growth. So my function is going to be 972 times 1 plus 0.015 to the t power. So 972 times 1.015 to the t power. And then if I want to find the number of students enrolled this year, well, I need to figure out how many years it's been since 2002. It's currently 2025, so that means that will have been 23 years. So 972 times 1.015 to the 23rd power. And we're talking about a population, which is people, so we need to round to a whole number. So it's going to be about 1,369 students. Moving on, I've got an investment of $12,000. That's A, that is losing value. So that tells me this one's going to be decay at a rate of 4% each year. So this time I'm going to subtract R. So I still got my A value, 12,000, and I'm going to do 1 minus 0.04 to the t power. So that will be 12,000 times 0.96 to the t. If I want to find the value of the investment after 9 years, I'm going to plug in 9 for t. And again, this is talking about money, so I'm going to round to the nearest cent. And that's approximately $8,310.41. Okay, lastly for this page, Mark bought a brand new car for $35,000 in 2008 if the car depreciates in value by 8% each year. Now, depreciate tells me that this is going to be decay. So the model for this will be that y equals 35,000 times 1 minus 0.08 to the t, which will be 35,000 times 0.92 to the t. So if I want to find the value of the car in 2015, well, that will have been 7 years after Mark bought the car. So plugging in 7 for t, 0.92 to the 7th power. And again, this is the value of a car, which is measured in money, so I'm going to round to 2 decimal places. And it's going to be about $19,524.63. Okay, then the last thing I want to draw your attention to today is our natural exponential function, where we have e to the x power. So e is called our natural base, and it's kind of like pi. It's got a never-ending decimal, and it's roughly 2.71828, and it trails on and on and on, kind of like pi does. Now, your parent function, e to the x, looks like your regular exponential function. Your domain, range, y-intercept, increasing, and horizontal asymptote all have the same features. And when do we use this natural base? Well, when we have continuous growth or decay. So the equation here looks a little bit different. A is still your initial value, e is going to be your base, and then you have your rate of growth or decay and time both in your exponent here. Now, r is going to be greater than 0 when the formula represents growth, and r will be less than 0 when it represents decay. So a person invested $1,000 into an account earning 10% interest every year, compounded continuously. So my function here, and that compounding continuously, is what tells me this is going to involve e. So that's going to be 1,000 e to the 0.10 t power. Now, if I want to find the value after 2 years, I'm going to plug in 2 for t. Now, you have an E button on your calculator. It's down here. Oops, sorry. It might be green or blue on yours, depending on the age of your calculator. But to get to that button, you hit second, and then that LN. So I'm going to show you. I'm going to calculate this by first typing in 1,000, and then second E. And then I can add my exponent, 0.10 times 2, and I get 1,221.40. So again, rounding to cents because we're talking about money. Okay, and then lastly, before I run out of time, radon 222 decays at a continuous rate. That's what tells me I'm using E of 17.3% each day. How much will be left if I'm starting with 100 milligrams after 33 days? So that function will be 100 e to the negative 0.0173 t. Again, it's less than 1 because we're doing decay. So after 33 days, 100 e to the negative 0.173 times 33. So 100 e to the negative 0.173 times 33, and I'm going to have about